Hello, class. This is Mr. Hart. And in this podcast, we want to start a unit on forces. Now, before we can get into forces, we have to start with a idea we call vectors. Okay, because forces are represented by vectors, and so we need to understand what a vector is and how it differs from the things we've already looked at. Okay, so let's just get right into the vocabulary of defining what a vector is. Okay, so up to this point, everything we've looked at is what we call a scalar. Okay, it's a physical quantity represented by a single value, whereas a vector is a physical quantity represented by a value and a direction. Okay, let me just give you an example really quick. Oftentimes we describe the time in a scenario or the speed of an object or its location, right? And so, for example, if I want to give you the time, I'd say that t equals, let's say, 3.1 seconds, right? So I give you a single value and a unit associated with it. Okay, so the value is 3.1, the unit is s, or seconds, right? With vectors, we need to be more specific because now we have a direction that's involved as well. So, for example, you may need to specify a force, right, which is measured in newtons. So the force is equal to 3 newtons, right? And we may need to say it's to the right, or to the east, or to this direction, whatever direction it may be. Okay, so now we specify a value. Okay, the value is 3. We specify a unit. The unit is n, or newtons. And then we give a direction, okay, to the right. And we'll see there's many ways we can express that, but this is a vector. So it's just like a scalar, but now we have a direction associated with it. Okay, so value, unit, direction. Okay, that's a vector. Okay, sounds simple enough, but we'll find there's some interesting things we have to account for when we do this. Okay, so first of all, let's talk about why we want to use vectors. Okay, so by including that direction in our representation, we don't have to do separate calculations. We can do our calculations without having to worry about the direction because it's built into our values, right? It's built into the numbers we're using. And so we don't have to break it apart into different directions and say, okay, well, these are two values, and we add those together, but wait, one's in a different direction. And if we just include those all in our description as a vector, then the math becomes easier. We can just account for it all at one time. Another way to think about it is we're basically just killing two birds with one stone. Rather than doing two separate problems, one for the value and one for the direction, we can just do them both at the same time. Okay? All right, so let's talk about all the different ways we can represent direction with vectors. Okay? So here's a table, okay, of things that we can specify vectors of. Okay, so we have an amount or value and a direction, right? An amount is a number and a unit, like 45 miles per hour, okay? And then the direction, we can say it in a couple of different ways. We could say, 45 miles per hour to the north. We could say 10 newtons down, like the cardinal direction down relative to the earth. We could say 100 meters. We can specify an angle, so 100 meters to the angle of 20 degrees north of east. Okay, we could just say something like to the right, 5 feet to the right, right? So we can give our values in many different ways because we have different things we represent, and we can give our directions in many different ways. We'll find later on that the most common way to do it is with an angle because you can be the most specific when you use an angle to describe it. Okay, so let's do a quick activity. Really quickly, I want you to think about the following things we've described in the past, the following quantities. And I want you to think if they're a scalar or vector quantity. Okay? So pause the video if you need to for a second. I want you to think through what each of these is. Is it a scalar or is it a vector? Okay? So we've already talked about time, and time is definitely a scalar, right? You can't specify direction with time. Time always flows forward, okay? And so you don't really need to specify that the time is flowing forward. You can just say what time it is or what time has passed, okay? Distance is also a scalar, okay? Because you have to account for the entire path, okay? If you remember way back when we talked about motion, right? Distance is every single path you take is accounted for, okay? So if you're going this direction and that direction and winding back around and coming through, you have to account for all that distance, okay? Whereas displacement is a vector because we just have to worry about the final and ending locations. And so we can specify where our starting location is and where our ending location is and use a vector to describe the direction of that ending location. Okay, so if I started right here and ended right here, okay, distance would account for any crazy path I took to get to the end, whereas with the displacement, we just say, look, we just went from here to there, okay, and you could say we went from, 25 meters to the northeast or whatever you want to say, right? But this is definitely a vector. We're specifying a starting location, we're specifying the ending location, and we're specifying the displacement between them, and we can specify what direction that was, okay? Then the speed is also going to be a scalar because it's just the distance over time, right? And again, if you think about driving in your car, it doesn't specify what direction you're driving, okay? When you're using your speedometer, it doesn't worry about that. Whereas the velocity is a vector because it's the displacement over time, right? So again, just depends on the ending and starting positions, and you can specify what direction you are heading when you find your velocity, okay? And the last of all, force is also a vector like we've talked about, okay? Because direction does matter when you're pushing an object, right? Which way you push the object is definitely going to affect which way it goes, right? So that's going to be an important vector, okay? So keep that in mind that in reality, when I was telling you about motion at the beginning of the year, I said the difference between distance and displacement is one's path dependent, one is not. But in reality, from now on, I want you to think about distance being a scalar and displacement being a vector. That's the more important distinction that we need to make rather than this path independence thing we talked about. Okay? But there we go. So now we got to start thinking about when we see something, is this a scalar or is this a vector? Okay? All right, let's talk about how we think about vectors, how we draw them, how we represent them. Okay, let's just start with one dimension to make it easy. Okay, so all the vectors we draw, we represent with an arrow. Okay, not just a line, but an arrow to show which one was the starting and which one is the ending. So for example, this arrow represents 100 meters to the right. Okay, and so you started here and you went there, so you end at the tip of the arrow. So when we draw vectors, we need to keep some sort of sense of scale, because in this problem, I don't have 100 meters to draw an arrow, right? I don't have a full track length on my paper to draw an arrow. Okay, so I'm just going to draw this length to represent the arrow, and that's totally fine, as long as I keep some sense of scale. So if this is 100 meters, then 50 meters to the right should be half that length, okay? So if we can, we try to represent vectors one-to-one, right? If it's talking in centimeters or whatever it is, try to represent them one-to-one, but if not, we just need to maintain some sort of scale. Okay, so if this is going to be 100 meters, then 50 meters needs to be half as long. Okay? And then we always draw the arrow, obviously, to the direction that is specified on the problem. Okay? So, if we think about adding vectors and thinking about vectors, okay, let's just go through some example scenarios. Okay? So a horse is pulling a cart with a force of 200 newtons, and a man is pushing the cart from behind with a force of 100 newtons. Find the resultant force. Okay? Well, this is a pretty simple problem. So we say, okay, we have a 200 newton force to the right, and that is pushing on the cart, and the man behind is also pushing on the cart, okay? And he's pushing with 100 newtons in the same direction, okay? Now, again, trying to keep some sort of scale, this arrow should be about half the length of that arrow, okay? But you'll see that the final result is 300 newtons, okay? And again, I don't really need to specify where the cart was, where the man was relative to the horse. All I need to specify is that the forces were in the same direction, okay? And I just do that by drawing two arrows, okay? And then in this problem, we have two resulting forces, but now they're in opposite directions, right? So one arrow is pushing with 200 newtons, okay, and the other one is pushing with 100, right? Now, again, I don't necessarily need to put exactly where they're referenced as long as I make the arrows in the right direction. So we have one that's 200 newtons, and we have one that is 100 newtons. And then if you add those two arrows together, because they're in opposite directions, they actually minus from each other. So you get 100 newtons. Okay? Basically, 200 newtons minus 100 newtons is 100 newtons. Okay? So I'm doing a lot of wishy-washy descriptions here. Let's actually look at how we draw this so that we don't even have to think about the numbers per se. We can just use the arrows to solve these problems. Okay. So here's our first rule that we get. Okay. Here's the first rule. If we have two vectors, okay, and we add them together, if we draw the arrows side by side, then the resulting arrow is the same length. So if I add A and B, I get an arrow or a vector of the same length of A plus B. Okay? Like in the first problem, you have two forces in the same direction. They're just going to add together to get you the resulting force. Okay? If I have two vectors in opposite directions, okay, you should get a vector that is this length minus that length. Okay, so if this was 200 newtons and this was 100 newtons, we should see a length of 100 newtons, right? You can imagine kind of taking this arrow right here and pasting it right there. If you can see, this distance is this vector right here on the bottom is this distance minus that distance, or this vector minus that vector, right? And so it should be about that same length. Okay. So when you have vectors in opposite directions, okay, that's what you're doing. You're basically just minusing the arrows off of each other. Okay? And that explains our two problems we just did. Okay? So I don't even have to think about the direction per se. If I draw the vectors correctly, the math should work out properly for us. Okay? And so again, that's kind of our goal for this lesson, is just thinking about things in terms of vectors and just drawing vectors. We're not going to focus on the math right now. We're just focusing on the vectors. Okay? Now that's pretty nice and easy, but vectors aren't always in one dimension, so let's get a little bit more complex. Okay? Here's a very important concept for drawing and adding vectors. Okay? Vectors always add according to what we call the tip-to-tail method. Okay, so if I have two vectors, A and B, okay, then I can add them together by putting the tip of one arrow to the tail of the next one, and then the resulting vector is the tip to tail of the whole thing. Okay, so I'm going to move A plus B out of the way for a second. So I draw vector A, then I draw vector B, okay, I put the tail of B to the tip of A, and then A plus B is this distance, or this vector, from the tail of A to the tip of B. Okay? That's our new vector. Okay? That's the resulting vector. Okay? So basically, if I have two forces pushing on an object, one in this direction and one in that direction, it's equivalent to one object being pushed in this direction. Okay? With that much force. Okay, and that's why this is useful, and we'll see this a whole lot when we get to forces, and that's why I want to understand them right now. Okay, let's look at an example problem. Okay, let's say I have the following vectors right here. Okay, I have A, B, C, and D, and I'm trying to add them all together. Okay, well, what we want to do is, again, we want to use the tip-to-tail method. Okay, we're going to try and we have all these different forces, or different vectors working on one object. What's the result? What's the complete total vector, total force on this object? Okay. Well, I'm just going to kind of copy and paste some of these guys. Okay. Move these around and put every single one tip to tail. So I put the tip or tail of B to the tip of A. I'm going to put the tail of C to the tip of B. Okay. And then I'm going to put the tail of D to the tip of C. Okay, like that. Now, let's move these all down a little bit. And again, this is kind of nice, right? I mean, it doesn't really matter the order we do this in, or how we do this, or where we draw it, right? The main thing is, as long as you have a tail of each vector to the tip of the next one. Okay, so now that's the tip to tail of all the vectors. So our resulting vector would be this vector right here. Okay, so adding all those vectors together gives us basically this arrow right here. Okay, now you guys probably don't have the convenience of copying and pasting all the different arrows. So let's look at another problem and just think of how we can draw this without having to manipulate all the arrows. All right, so here's another example problem. And again, I was just copying and pasting the actual arrows. You guys don't have that convenience when you're doing this on paper. So let's try this again, and I'll try and mimic more of what you guys will be doing on your homework, okay? So here are 4 vectors, okay? I want you to kind of memorize these, okay? And we'll go to a blank whiteboard. But we want to just, again, use the tip to tail method and add these vectors together. Okay, so let me pull up the whiteboard. All right, so we're going to just draw each one of these vectors. So vector A looked about like this. Okay, so the southeast direction, about that length. Vector B looks something like this. Okay, so on your homework, you're going to want to be more exact on your lengths, but again, put the tail of one to the tip of the next. Vector C was just this short little vector going straight up like that, and then vector D was a long vector like this. Okay? So tip to tail, that looks good. So our resulting vector is the difference between the tail and tip of A and D. Okay, so it would look something like this. Okay, so almost straight across. That's our resulting vector. So if those 4 forces were acting on one object, the resulting force is just one force about to the east direction. Okay, that's very large. Okay, but that's how we add vectors. It's that simple. Okay, so tip to tail method. You want to make sure you got that down because it's going to be very important when we get to forces. All right, and I want to bring up another point, and I want to make sure we're clear on this. Does it matter the order we add the vectors in? And the answer is no, it doesn't matter. If I put those vectors in any given order, you'll get the same resulting force. It's commutative, if you know what that word means in math, but it just means we can change the order up no matter what we do. As long as we use the correct method, we'll always end up with the same resulting force. Okay? Alrighty, let's do one more problem to show you exactly how you want to do your homework. Now, in the problem, it says add the following vector. We have 5 centimeters south, 8 centimeters east, 3 centimeters north, and 2 centimeters west. Okay, so this is being very specific about the scale. So we need to be very specific with how we measure this. So you're going to want to use a protractor. Okay, I have some in class. If you don't have one, you'll just borrow one from me. And we're going to want to actually measure the length of these vectors and use that to specify the exact resulting force. And then we can also use the protractor to get an exact description of the direction because we can use an angle. Okay, so I'm going to try my best to approximate this on my screen. I don't have nearly enough space to do these full dimensions, but I will try and make this as accurate as possible. Okay, so 5 centimeters south, get our protractor, put on your paper. Okay, and that would look something like this. Okay, then we have 8 centimeters to the east. So again, protractor. Make sure you're using a proper scale. It's going to look something like that. Okay, then 3 centimeters to the north. Again, I'm not promising it's perfect or anything. And then, last of all, 2 centimeters to the west, which would look something like that. Okay, so, again, you're going to want to be more exact. It's kind of hard to do it on a computer screen, okay? But you'll use your protractor or your ruler to get the exact values and draw these as best you can, okay? So our resulting vector will be the difference between, again, the tip and tail of our last 2 vectors, which will give us something like this. Okay, so that's our resulting vector. Then we can use our protractor, again, to measure its exact length. Okay, and it looks like this is going to be about, assuming my measurements were okay, this will be about 7 centimeters in length, And you can use the protractor to get the angle. Just make sure you have the little hole. Okay, where that little hole is where you're going to put your tail of the resulting vector. So that will be this spot right here. And then just compare it to the tip of the arrow. Okay, so if I put my protractor there, then I get an angle of about 25 degrees. Okay, 25 degrees. So that's relative to this. Okay, so that angle right here is about 25 degrees. Okay, and so you may need to specify that it's to the south. Okay, so 25 degrees. I'd write this as south of east. Okay, basically meaning that we changed our direction 25 degrees south instead of going straight to the east. Okay, so this is 25 degrees south of east. Don't worry so much about this part. I'm mostly concerned about getting the angle correctly with the protractor. Okay? Alrighty, but that is your homework, just adding together vectors. Use the protractor to get the exact lengths and keep the scale accurate. Use the tip to tail method, and then use the protractor to get the angle. Okay? But that is it for this lesson. Hopefully that all made sense. Let me know if you have any questions, and thank you for watching.